So that was the sound of an MRI scanner, and you probably had the experience at least once of lying in a big claustrophobic donut-shaped scanner that can produce high contrast images of your knees, your abdomen, or even your brain.
Magnetic resonance imaging was introduced in the 80s and is considered one of the major innovations in the world of diagnostic radiology. MRI uses the complex but well understood phenomenon of nuclear magnetic resonance imaging to map water within the body. As water is used in different ways that can vary across organs and can be altered in disease, MRI is a very flexible and non-invasive tool to image the human body.
And while lying in that scanner, have you ever thought, what if this gigantic machine could be portable? What if we could have a portable MRI scanner that could be brought to the point of care in places where having a room-sized MRI scanner would not be possible?
I know, even the thought of it sounds crazy, right? Well, today's episode will tell you the story of how it is indeed possible to shrink room-size MRI scanners.
最前沿的科学研究
Science
Innovation und Wissenschaft
مدى تكنولوجيا
كشف جديد
Pesquisa
Discovery. Rehashing science. Hello, I'm Shen Ning.
And I'm Mehdi Jurfi, and you are listening to a new episode of Science Rehashed.
If you're enjoying the show and you want to help us keep making the content, please consider becoming one of our patrons on Patreon. Find us at patreon.com/join/science-rehash to become a patron for just $3 a month. Or you can become a VIP patron for just $5 a month. Our first 10 VIP patrons will receive a free Science Rehash water bottle.
And don't forget to visit us on Twitter to rehash the episode with all of us. Join the conversation with us at Science Rehashed using the hashtag SREpisode. See you all there.
And we're back with another Rehashing Science episode, and I'm really excited about our guest today. We interviewed Clarissa Cooley, a fantastic scientist at the MGH Martinos Center for Biomedical Imaging. Clarissa's research focuses on the development of high-impact imaging systems based on new approaches to hardware, image encoding, and signal processing. Today, she'll tell us about her challenge to develop a portable, low-cost MRI brain scanner.
That's really impressive, Shen, and I can't wait to hear more from Clarissa about that. And I'm not the only one. Today we have Jasmine with us, one of our Science Rehash ambassadors from Italy. For her PhD project, Jasmine uses MRI to study structural changes in the brain. And she could not wait to sit in on the interview with Clarissa. Hi, Jasmine. How are you doing today?
Hi, Mehdi and Shen. I'm so excited to be here for the interview. I read a lot of papers in preparation and had noted a lot of questions on the PDFs, but now I can't seem to be able to find them. I have so many research articles on my desktop, all with truly awful file names. I'm not even sure what folders half of them went into.
Keeping all of that stuff organized by hand is a losing battle. I use papers to help me manage all my references and PDFs across all my devices. It matches all of my articles with the correct metadata and brings in the article's supplements automatically. It also helps me to find the latest papers and gets me to the full text fast. It's even got full citation writing support for Word and Google Docs.
That's great. Where can I get papers?
Well, Jasmine, the good news is you and Science Rehash listeners can try Papers free for 6 months by heading over to papersapp.com/science-rehash. That's papersapp.com/science-rehash.
Yeah, that is awesome. And if our listeners want to follow along for this episode, they can find the article that we're talking about on our website, sciencerehash.com, in the episode section.
All right, let's now meet our guest for this episode.
My name's Clarissa Cooley. I'm an instructor at the Martinos Center for Biomedical Imaging. My background is in electrical engineering. I went to MIT for undergraduate and graduate school. When I was an undergraduate there, I started doing undergraduate research in a bioinstrumentation teaching lab. And I was helping to make homemade instrumentations for students to use in the class. And one of the ideas was to build a classroom MRI scanner for students to use in the class, actually. And so this was really my first introduction to MRI. And that's what really started my career in MRI medical imaging. That was about 12 years ago at this point.
When did you become interested in the idea of developing portable MRI systems for clinical applications?
So I was working on the classroom system at MIT, and I, learned a lot about MRI physics and sort of a self-taught start to MRI hardware as well. And I found it, really interesting. I loved the feeling of sort of building a system from scratch, but it was very far removed from any type of medical application. So when I started my PhD, I sort of jumped at the chance to work at the MGH Martinos Center, where people really are doing groundbreaking engineering work that's applied to clinical application. And my PhD thesis advisor, Larry Wald, proposed a project to me for this sort of crazy helmet-style portable MRI scanner for brain imaging using permanent magnets. And I thought this was incredibly exciting and have basically been working on these sorts of portable MRI scanners ever since.
That's a fantastic journey. Thank you for sharing it with us. It seems to me this crazy project came true, as a few months ago you published a fantastic paper in Nature Biomedical Engineering titled A Portable Scanner for Magnetic Resonance Imaging of the Brain. In this paper, you and your team reported the design, testing, and validation of a portable MRI brain scanner prototype. Could you please tell us a little bit more about the idea and the development of this project?
Yeah, so I guess first off, I think imaging with MRI is sort of an amazing thing. It's really safe, non-invasive, and it doesn't use ionizing radiation. It allows us to visualize anatomy in the body with tremendous detail and a variety of contrast mechanisms, particularly in the brain. The soft tissue contrasts we can visualize is unparalleled by any other imaging modality. But the problem is that conventional MRI scanners are very, very inaccessible tools. They're giant instruments weighing several tons, and buying and installing scanners can cost millions of dollars. And this really means that diagnostics with MRI is completely not an option in many, many cases here and globally. Even here at MGH, where of course, we have MRI scanners and so many resources. There are cases where MRI imaging is not used because patients are just really sick and not stable enough to be transported to the radiology suite. And so this is what really motivated this work on portable, low-cost MRI as a way to bring MRI imaging to the patient for point-of-care imaging, whether that means to bring it to the patient's bedside or to easily site it in a rural clinic with low resources. So making this type of technology widespread could really have a huge impact and allow MRI imaging for new applications and in places where it was completely unavailable before. And from an engineering perspective, it was a really fun and exciting problem to work on. So the question of how do we transform these giant machines with all of their safety and infrastructure requirements into something that we can bring into a patient's room on a cart.
So when you were working on this problem, I'm sure in order to kind of reduce the size of the MRI machine, you had to make a lot of decisions in terms of what to cut down, what to include in the machine. So what kind of decisions did you have to make in terms of the design of this tool in the process?
I think that a really important aspect of our approach was, we tried to kind of think outside the box instead of just thinking about scaling down a conventional sort of MRI scanner architecture. We tried to sort of reimagine the way that MRI is done. And so this started really with the magnet design. Instead of using a large full body superconducting magnet, we used a small permanent magnet array that fits around the head only and is specialized for head imaging, brain imaging only. So it sort of reduces the applications to a specialized application space. But it allows us to really produce this very portable design to bring MRI to places where it was not available before.
To get a better understanding of what you are saying and how you went and made these decisions for designing the portable scanner, can you walk us and our audience on the basics of the conventional MRI machines?
Sure. So most conventional scanners use a large superconducting magnet to create the main static field called the B0 field. And the strength is usually 1.5 or 3 Tesla, and it's a very uniform field. And the strong uniform field basically aligns the magnetization of the protons in the water molecules in our body. And then when we excite the protons with an alternating magnetic field, the protons precess at a characteristic frequency that's proportional to the static field strength. And we can actually measure the alternating magnetic field produced by the protons in the body with receiver coils. So that's where the MRI signal comes from. To acquire an image, we encode the signal using magnetic field gradients, typically produced with gradient coils in the scanner. And so because the frequency of the MRI signal is proportional to the static field, when we apply the field gradients, this causes different parts of the body to produce signals at different frequencies. And then we can use this information to figure out where the different signals are coming from to form the image. So that's sort of the basics of how MRI scanners work in the conventional sense.
And why do conventional scanners need to be so large and expensive?
The reason they're so large is to make a really strong uniform field that is sort of body sized. You need a really big magnet. And the conventional scanners have a very uniform field, like only a few parts per million variation. And so to achieve this very high field strength that's very homogeneous, they use these superconducting magnets with liquid helium cooling, which also adds to the cost and the complexity. And then the gradient coils tend to be quite heavy. They use big bundles of copper wire to produce these strong field gradients that are then switched on and off quickly using big power amplifiers. And then those need water cooling systems. And so traditionally, we want any field variation to be dominated by the field gradients for image encoding. And this means that we need the B0 magnet to be really uniform or the gradients to be super strong. And both of these things contribute to the size and the weight and the cost of the system. Another way of looking at it, though, is that contemporary MRI scanners are really big and expensive because they're just really powerful instruments that have been really designed to maximize the image quality and, are able to image any part of the body with an incredible array of contrasts.
So how big is a conventional MRI machine and how big is a portable one?
They weigh several tons. And, the size maybe, I'm not really sure, maybe 3 by 3 meters or something like that. But really, when you're thinking about the size, you have to think about like the whole radiology suite that it's sited in. It's not just the scanner itself, it's the whole room and the equipment room and everything that goes into that. Our prototype scanner, including everything, weighs about 200 kilograms. And the size of the magnet is about 40 by 40 centimeters.
Fantastic. And what about the cost comparison?
So, typical scanners, the cost of the scanner with the installation, I think it varies a lot, but it's on the order of millions of dollars. Our scanner, with all of its components, is on the order of $20,000.
That's really incredible. That's fantastic. Hey listeners, I hope you're enjoying this episode. As usual, I'll now be reading a new review from one of our listeners. And if you also want to tell us your thoughts, head over to Apple Podcast and let us know what you think about Science Rehashed. Today, our comment is from Lorben27, who says, "This podcast is perfect for anyone who's interested in science, but doesn't have time to sift through the papers for hours. Easy to follow and really interesting combos." Thank you so much, Lorben27. Listeners, now if you want to be featured next, don't forget to leave us a review on Apple Podcast. Wow, it's really incredible to think that hospital scanners costing millions of dollars and weighing up to 3 tons can be shrunk down to the size of a television that we can actually transport on cart. And as Dr. Cooley just explained to us, this change can be achieved by reimagining the magnet design and making it specific for brain imaging. To get more into the details now, what is the spatial resolution of the images acquired with this portable scanner, and what can you see / what can't you see?
The image quality of conventional scanners is higher than with this scanner. The high field strength increases the signal to noise ratio, and therefore the resolution that you can achieve in a reasonable amount of time. But our goal with this system is really not to compete with the image quality of high field systems. It's really to sort of provide the specialized scanner option with lower image quality, but a new application space, and allow it to be used in new places where MRI wasn't available before. And the idea is to just really provide image quality that is good enough to sort of answer the diagnostic question.
And is this difference in image quality related to the homogeneity of the magnetic field? You already mentioned conventional MRI scanners try to have a high homogeneous magnetic field. So how does this differ in the portable system?
Yeah, so that's one of the main things about our scanner that's different from other scanners. We decided to relax this constraint on the homogeneity of the magnet to allow us to design a much more compact magnet. So it's really, really hard to create a really homogeneous field with a small magnet. So we kind of decided we're going to make this small magnet. It's going to have an inhomogeneous field. And we decided to use that to our advantage and actually tailor the field variation into an image encoding field. So in that sense, the image encoding field that we create with the field inhomogeneity of the magnet also allows us to eliminate some of the other electronic component, namely one of the gradient coils.
And is there any disadvantage with this using inhomogeneous field compared to the homogeneous?
Yeah, so using an inhomogeneous field for MRI, typically the disadvantage is that it causes image distortion. Generally you want a very homogeneous B0 field, so then you can use these very linear field gradients for image encoding. So when you have sort of random field variation of an inhomogeneous magnet, you start to get distortion in your images. So to account for that, what we do is we actually measure all the magnetic fields. We map them out from, including the B0 field and also our encoding fields. And then we use these measured maps to reconstruct the images to reduce the distortion. Another sometimes disadvantage would be that if you're using an inhomogeneous magnet, you have a wide frequency range that you have to excite and measure. So there are additional technical hurdles associated with that.
And I was wondering, how stable is your portable prototype with respect to the electromagnetic interference coming from the surrounding environment?
So our portable scanner is, because it has a low magnetic field, and because, we want to be able to sort of move it around, it's possible that different environments might affect the magnetic field and change it. And so there are different ways that we could account for this because it could introduce distortion in our image. One way is that, when we move it or we resight it for imaging in another location, we can measure the field again and use that in the image reconstruction. But a simpler and probably faster method would be to use just probes, field probes that remain in the magnet that would measure any changes. And then we could use that in the image reconstruction as well.
Where do you see the first application of this portable scanner?
I think that the most beneficial applications are really to bring the scanner to the patients who cannot be brought to the scanner. So patients who are unstable or kind of need continuous monitoring in the ICU, for example, or the neonatal ICU. So you could bring the scanner to the patient's bedside and do imaging there. Whereas before, there wouldn't really be a way to, or you'd have to wait for the patient to recover or become stable enough to transport to the scanner. And I also just think that just the ability to easily cite this low-cost, scanner that doesn't require special power installations or cooling installations in a rural clinic or anywhere where there are low resources would also have a really big impact.
And how far this from the reality, you think?
I think it could be very soon. I mean, we've started doing some patient imaging already, and we have some technical problems that we're still, working on before we feel like we could bring this into a patient's room. But I think that I can discuss some of these problems that we're working on actually. So the images that I showed in the paper were acquired inside of a shielded room that reduce electromagnetic interference in the images, and so this is important because electromagnetic interference can be picked up by the receive coils in the magnet, and that results in just lower image quality, basically. And so to start with, we acquired our images within a shielded room that reduces this, but we're currently working really hard on another method that uses external probes to measure the interference and retrospectively remove it.
And I have two different thoughts regarding the implications of these prototype. Do you think it will become reality to use these portable scanners in war zones, for example, where it's impossible to bring injured soldiers to hospitals? Or for hospitals in low-income countries that just cannot afford conventional expensive MRI scanners?
Yeah, definitely. I think that's those are really important applications. We actually, the very first funding source for this project was through the DoD. For the idea of a battlefield scanner for traumatic brain injury. And I think that that's, definitely a really strong application of this. And, equally, I think being able to easily cite this in low resource areas would be really, really, really helpful. I think that part of our design was to make sure that this scanner could be operated from just a standard power outlet. So, meaning you can bring it into a patient's room and basically just plug it in and start using it. And that same idea, just makes it really easy to install sort of at anywhere.
That's really great to hear. Additionally, what kind of training is required to use this device? Is this something any of us essentially on this call can just go over there and plug in the device and put it on someone's head and then be able to use it, or will it still require trained staff to operate it?
Yeah, that's a really good question, and I think that is that's something that we sometimes forget about how important the availability of trained personnel for operating the scanners is also, not just the hardware itself. I'll say that like with our prototype that's in the lab right now, it would not be very easy for one of you to just jump in and start using it. But I guess the inspiration, the goal is to make it that way, to make it sort of just like a plug and play, like push a button for one sequence, push another button for another sequence, and like have an image pop up. Like that's the ultimate goal.
It sounds like science fiction, but do you think it will be possible in a few decades to buy a portable MRI scanner the same way we buy a pregnancy test now, and have AI incorporated in the system so that you could scan the brain and do early stage at-home diagnostics?
That's a really interesting idea. I would say that that's definitely not like our current goal that we're thinking about with the scanner, but I think that it's not impossible. If the cost is low enough and the interest is high enough, I think I think that there is, there could be a path in the future to make this so that it's like that accessible and that safe to use.
But I wonder if that's a really interesting point, Maddie. But I wonder if that's a good, necessarily a positive thing, because, you reading and trying to interpret your brain imaging may not mean that may scare you a little bit because you don't know exactly what to look for, But, a trained personnel may be a little more knowledgeable in terms of what to be worried about, what not to be worried about. Whereas having that, it'll be a great resource if you yourself can interpret it, or the machine itself with the AI algorithm can kind of give you hints of or red flags if something needs attention. But I almost want to say, I don't know how physicians, for example, would feel about giving patients that ability to interpret their own imaging results.
Yeah, I think there is some danger there for, causing maybe unnecessary anxiety, and also, sort of, increasing, kind of unnecessarily increasing how much we're spending on healthcare.
And I know you first developed these prototype mainly thinking of applications for traumatic brain injury. Have you thought of expanding the development of portable scanners to image other parts of the body?
I have thought about this a little bit. I think that there are actually some commercial scanners out there for extremities specifically. And I think that that is a good application as well. We have not actually, I think we could actually do some extremity scanning in this scanner, and we haven't done that yet. From my brief conversations I've had with sort of orthopedic applications, the type of resolution that you need for sort of like surgical planning is very, very high, very stringent. And so I think maybe a low field scanner would not be the right choice for that application.
So Dr. Cooley, you're also involved in the magnetic particle imaging hardware development effort at Mass General Hospital. So can you tell us a little bit more about this project and what your contribution to it is?
So magnetic particle imaging is it's a completely different imaging modality than MRI. It sounds similar, but it doesn't use MRI scanners at all. It's a really new imaging modality that has not actually been used in humans yet. And so in this method, what we do is we inject magnetic nanoparticles into the blood, And we use similar magnetic field coils and technology to measure the magnetic field from the particles themselves that are injected. And the big advantage of this method is that the magnetic field that we can measure from the particles is just orders of magnitude higher than what we measure from the protons in the body. And this could allow us to get a much higher contrast to noise ratio for different applications. We've been really interested in looking at functional neuroimaging with MPI. And the idea here is that we inject the particles into the blood, and they act as a blood volume agent. So in the brain, when you, for functional neuroimaging, when your neurons are firing, you have an increase in the local blood volume. And you can sort of map this increase in blood volume to do functional imaging. And so we want to do this with MPI, and we think that with this method, we can achieve a much higher contrast to noise ratio than current methods that are out there. My contribution to this project so far was I worked on one of the first devices for this to measure dynamic blood volume changes in rats using MPI. And so that was sort of the starting place. And now our team has moved on to building a full-scale human-sized system for doing this type of functional brain imaging in humans. And this is sort of the first of its kind.
I was wondering whether you envision that in the future most MRI systems will be equipped with permanent magnets, maybe in slightly bigger version than the one you prototyped. And I guess this could help get rid of the expensive cooling down systems.
Yeah, I think the use of permanent magnets has the major advantage of, number one, not requiring power, and number two, not requiring cooling. So the superconducting magnets, they require cryogenic cooling with liquid helium, and that has been a problem in the past. So I think that, that's definitely an advantage of this system. I think that there are also new designs out there that use high temperature superconducting magnet that also helps with this problem. And also scanners, I think, are becoming better at not boiling off helium, so they don't need to be refilled as often. But yeah, I think that permanent magnets are this is a non-issue for permanent magnets.
Besides doing science, what do you do in your free time?
The biggest thing I do with my free time is I'm a mother. I have two kids, and so I spend as much time with them as I possibly can. They're 3 years old and 9 months old, so they also require a lot of time and attention.
Wonderful. I just want to say thank you again for joining us today. It was a pleasure and honor talking to you, and for this advancement in the MRI scanner.
Thank you so much for joining us today.
All right. Yeah. Thank you so much for having me. It was really nice to talk to you all.
That was a very exciting conversation. I really think one day we will be able to have MRI scanners at home.
Yeah, and it's really incredible to be able to witness such enormous technological advancements in healthcare. Thinking about how fast we've gone from the first personal computer to laptops now, it might not be that long before your vision comes true, Mehdi.
That's absolutely accurate, Shin. Until then, I will keep following these scientific developments very closely.
And I'm sure you will, Mehdi. Listeners, thank you for joining us for another episode of Science Rehashed. If you enjoyed this episode and would like to hear more about Dr. Cooley's research, check out her talk at Open Box Science webinar on Thursday, June 17th at 12 p.m. Eastern Time. For more information, follow at OpenBoxSci on Twitter. Remember that you can support Science Rehashed by becoming one of our patrons on Patreon. Visit patreon.com/join/Science Rehashed to join. See you next time. Thank you for listening to another episode of Science Rehashed. This episode was written and produced by Kira Maffei, sound edited by Sophia Nastri, and mixed by Jared Warsoff. The cover art for this episode was created by our creative director, Emma Brand. We would also like to thank ReadCube for sponsoring this episode and providing a free 6-month subscription to papers to our listeners.